All right, so we've done polynomials. We've talked about generic power series. Now we're going to be specific with our power series and go right into our Taylor series. So let's talk about our definition here for Taylor. And I'm going to go ahead and put /Maclaurin, M-A-C-L-A-U-R-I-N, Maclaurin series for a function. That's a U function. All right, so here it is. Suppose the function f has derivatives of all orders on an interval centered at a point A. The Taylor series for f centered at A is this. Exactly what we saw from before, scooting this up just a little bit. F of A plus f prime of A times x minus A plus the second derivative centered at A over 2 factorial times x minus A squared plus more of that. Now that's our polynomial, right? That's our Taylor polynomial that we already talked about. But when we did our Taylor polynomial, we did specific terms, like specifically here. Now we are expanding this and saying, okay, this is going to be equivalent to my series, where I'm going from 0 to infinity, f to the k of a over k factorial x minus a to the k. All right. Here is our Taylor series. So it is this polynomial, and then this polynomial is going to give me that series. Now we said Taylor and Maclaurin series. Here's what's special. It's a Taylor series centered at 0 is called a Maclaurin series. That's it. So a Taylor series centered at 0 is called that Maclaurin series. So notice this. This is the power series where this is that C sub k where we had that coefficient. Now we specifically are saying you have power series, that's my big umbrella. Under that big umbrella, I'm going to narrow it down to a Taylor series where I'm going to denote this as my C sub k. Then I'm going to take a Taylor series, narrow it even farther, and say when A is equal to 0, right, I'm centered at 0, then that's specifically called a Maclaurin series. All right? These Taylor series and these Maclaurin series are quite helpful. All right, let's do some examples. I'm going to come to this new page because they take some room. All right, so let's do it right now. Here's example 1. We want to find the Maclaurin series and the interval of convergence. Okay, so here's example 1a actually. I'm going to have my function is a cosine of x, and because it says Maclaurin, what is my center? Yes, so automatically A is equal to 0, and we've got that. Now this is what we're charged with. We want to find the first 4 non-zero terms. Here is how you find a series. First of all, you find the polynomial. Whatever you get for that polynomial, that is your Taylor polynomial. So just like back here, I had this polynomial. And then we are going to use that polynomial to find patterns, which is why I told you before, don't ever multiply that out because that's going to help with our pattern. So use this polynomial to find a pattern, and that's how we come up with our series. So this is all about finding patterns. And so the first four non-zero terms specifically is what we're going for. Okay, so we're going to do the exact same thing here. I have in finding the derivative and my nth derivative centered at 0. So you always start with 0, and then I have cosine. So I know I'm at least going to have these terms. So I've got cosine. So cosine at 0 is 1. All right. Then look at what happens. The derivative of cosine is negative sine. Well, what's sine? Excuse me. What's sine at 0? 0. So is that going to count in my first four non-zero terms? No, but you have to keep going because your derivative is built upon the previous one, okay? So then I have the derivative of negative sine is negative cosine, which will give me a negative 1. So I know I'm going to have several more that I got to get through here. I don't know, let's just number some out and see how this plays out. So negative cosine, the derivative of that is going to be sine, which we know is 0. The derivative of sine is cosine. So here I have 1, 2, 3, so I need one more. So, ooh, perfect, nice. So I have the derivative of cosine is negative sine, and then this is negative cosine. So now I have first four terms, non-zero terms that we're looking at. All right, so let's play this out. So we know that our polynomial formula here is going to be the nth derivative at a over that n factorial x minus a to the n. So that's what I'm looking at for my polynomial, right? Let's do it. Okie doke. So my first term, this is divided by 0 factorial, to the 0, all that stuff. I'm just going to put a 1. My second term is 0. 0 times anything is 0. So for now, I'm just putting a 0 in there just so that you can see what's happening. And I like putting zeros in there the first time I do it because then that always keeps me honest with my n values. So this next one's going to be negative 1 over 2 factorial and then x minus 0 squared. So x minus 0 is, we've got that, plus 0 plus 1 over 4 factorial x to the 4th plus 0 plus negative 1 over 6 factorial x to the 6th. And then it goes more from there, right? So x minus 0, so this is the same thing as x minus 0 squared, right? And so on and so forth. I'm not going to write all those out because x minus 0 is just an x. Then clean it up a little bit. So if I have this polynomial, this is 1 minus a 1/2 x squared, right? Plus, I'm going to leave it as a factorial. 1 over 4 factorial x to the 4th because my goal is to find patterns. Minus 1 over 6 factorial x to the 6th. And the reason for the first four non-zero terms is so that you can start seeing that pattern, and it usually takes about 4 terms to pull that off. All right, so tell me some things that you're seeing with this. So now focus just on this part because I'm going to make my series here from 0 to infinity. And what do you see about the signs? Yeah, they are. They're totally alternating. So I'm going to have negative 1 to the k. All right. What do you see about this denominator? Even, right? So I'm starting here with this 0, 2, 4, 6. So my pattern is going to be 2k factorial. Do I have to put parentheses around all of 2k? Yeah, you do, because that whole thing is a factorial because I want to make sure that that is even. Okay. Then x, I know this is Maclaurin, so technically this is x minus 0, right? Oops, I have no idea what was going on with that. So that's technically x minus 0, which we know is, you don't have to write a minus 0. But what do you know about the exponent of x? It's even also. Oops. And that is my series. So there is my series. But I am charged with finding the series, the Maclaurin series, and my interval of convergence. Well, I'm out of room on this one, so let's go down here to this next page and find that interval of convergence. So given this series, I know k is going from 0 to infinity of negative 1 to the k, x to the 2k. This is over 2k factorial. Okay, so this is my cosine series. Now I'm looking at this and you have to say, oh, okay, well, I have to find my interval of convergence. How do I find my interval of convergence here? Yes, we're back to that same thing that we did. So we're kind of combining the first two sections here in this chapter to work it all together for our Taylor series. So for this one, because I have a factorial, I know that I'm going to be using that ratio test. Okay, well, let's do it right now. I have my limit as k approaches infinity here with my ratio test of negative 1 to the k plus 1, x to the 2 times the quantity k plus 1 over 2 times k plus 1 factorial times 2k factorial over negative 1 to the k and x to the 2k. Now here's the deal that I want to point out. With this, you are only plugging the k plus 1 in for the actual k value. All right, so you're going to have to work that out. Now for these negative ones, the absolute value is going to go away. Right, so I'm just not going to mess with that. For here, I get this exponent as x to the 2k plus 2. So I'm going to skip a step and I'm going to say x to the 2k times x squared, because this exponent is actually 2k plus 2, right? If I distribute this one, this is also 2k plus 2 factorial. So I'm not going to write out every single step because you got this. So this is 2k plus 2. Ooh, I have to write my limit, though, for crying out loud in a bucket. 2k plus 2, 2k plus 1, and then 2k. You have to go down in value, right? If you start off with plus 2, minus 1 is 2k plus 1. Minus 1 is 2k plus 0. That's where those come from. And then you can cancel this stuff out. So now I'm left with the limit as k approaches infinity here of x squared over 2k plus 2 and 2k plus 1. Well, what happens when k goes to 0? Oh, for crying out loud. I already said it, didn't I? When k goes to infinity, the whole thing goes to 0. Good, which we know is less than 1. And then we have absolute convergence. Remember, there's 3 criteria, or 3 options, I guess, for convergence. You can have absolute convergence, you can have an interval, or at a point. And this one is absolute convergence. So we have our series from 0 to infinity, negative 1 to the k over 2k factorial times x to the 2k. I don't really need to put parentheses around that x, but whatever. My interval of convergence is absolute convergence, so it's infinite. And there it is. All right. This is the Maclaurin series for cosine. Now, let's talk for just 2 seconds here. Think back to your trig days. I know it's been a while, but you can do this. Think back to your trig days. Cosine, was that an even or an odd function? It was an even function. Do you remember that? So if I'm looking at my graph here of cosine, it starts up at 1 and goes down and does its thing, right? Starts up at 1, goes down and does its thing. An even function means it's symmetric about that y-axis. Cosine is an even function. Ah! Check out that series. This all relates, guys. This all relates. That should make you happy. This is an even function. Well, no doy. We already knew cosine was an even function. Guess what? It just keeps following us. All this stuff you learned, we're just adding to it. Previous information into the current lesson. Nice.